Hello everyone, and welcome to the Physics Hour, a weekly event to explore different fields of research in physics and ask leading scientists some of your burning questions. My name is Simone, and we also have Annie here to help with the Q&A after the talk. Before we begin, many of us are likely to be tuning in from different places, but I'm coming from Montreal, which is situated on the land which has long served as a site of meeting and exchange amongst Indigenous peoples, including the Haudenosaunee and Anishinaabe nations. I acknowledge the diverse Indigenous peoples whose presence marks this territory from which I'm joining you today, and encourage everyone to learn more about the land that they live and learn on through the links posted in the chat. The Canadian Association of Physicists is the voice of Canadian physics, representing physicists in all parts of their careers. The CAP provides leadership and support to the Canadian physics community by celebrating Canadian physics achievements, keeping members up to date, and by running various initiatives like the ones you see below. The CAP Student Advisory Council was formed in 2019 to create a strong student voice within the CAP. We're an egalitarian, diverse, inclusive, and action-oriented group which seeks to represent, support, and unify physics students across Canada. Some initiatives we're currently working on include advocating for increased student funding, advertising student opportunities through our website and social media, and interviewing physics students across Canada to understand how we can best serve the community. If you're interested in learning more about what we do, I encourage you to browse our website. We represent all physics students in Canada, so please get in touch with us through our email or social media and share your voice. Now, I'm very pleased to welcome today's speaker, Professor Aaron Vincent.
Hi, thank you very much for having me. And thank you for the nice land acknowledgement. I'd also like to acknowledge that I'm speaking to you from Kingston, Ontario, near Queen's University, which is situated on traditional land of the Anishinaabe and Haudenosaunee people. And I'm grateful to be able to speak to you from these lands. Now, I'm going to tell you about, as you've read from the title, finding dark matter in the sun with Monte Carlo simulations with random walks. So this started as a slightly sarcastic tweet, and I'm not going to explain the joke. Instead, I'll tell you a little bit about what I do in most of my research at Queen's University before getting into the topic at hand. So this is work that is not done by myself. It's been done with, so I'll tell you a lot of background, a lot of work that was connected in some way or another with all of these people from all of these different places around the world, especially Hannah Banks, who did most of the simulations for this, and who put in a lot of effort in the paper that I'll be talking about. So I am an astroparticle phenomenologist, and I'm going to break that down for you. Astroparticle kind of explains itself. I try to understand what astrophysics or astronomy tells us about fundamental physics, how we can use astronomical observations to try to understand particle physics, and how we can use our understanding of particle physics to go and figure out what's going on in the cosmos. And the second word's a bit weirder. Phenomenology is, in physics, means sort of an in-between state between theory and experiment. So I'm more of a theorist, but a lot of what I do is trying to connect the observables that would come out of the theory of fundamental physics to what we would actually see in data, and taking data from various experiments and testing theories with that data. So astroparticle phenomenology is a really great field if you are very indecisive. So here's an outline of my talk. I'll only spend about 1 hour on each of these points. I think that's not allowed. I'll tell you about dark matter. I'll tell you about dark matter in stars, what dark matter does to stars. I'll tell you that everything that's been done so far is wrong, and the process that we're taking to try to fix that. Now, the work that I'm going to describe is kind of an in-the-middle work. So it's not discovering a new idea or a brand new idea or a brand new field, and it's not the end result where we've taken some observations and we've ruled out dark matter, or we haven't, or we've found dark matter, or we haven't. But it's the process of actually understanding the physics of what the theory tells us based on all the observations that we have in order to go and better look for dark matter out in space, in stars in particular. So let's start with dark matter. This image you may recognize. This is a recent image from last week, taken by the James Webb Space Telescope, JWST. And it's a deep field image of just a load of galaxies. Ignore these foreground stars here. But each one of these little streaks here is a gravitationally lensed galaxy. And what it's telling us is that the big globular object in the middle is so massive that it's lensing, it's curving the light towards us. The light which would have gone outwards is being bent back towards us and distorting our view of these galaxies. Now, the thing is, if you count up all the luminous stuff, you count all the galaxies and all the stars inside this blob, there's not enough mass there to actually account for all that gravitational lensing. There's some missing mass. And one of the main pieces of evidence that there's this missing mass traditionally comes from what are called rotation curves, which is just you watch a galaxy spinning, you look at the Doppler shift, the red shift or the blue shift of gas as it goes away from you, if it's spinning away, or towards you, it's spinning towards you, and you can figure out what speed that gas is going at. And what we see is if we go from the inner parts of a galaxy outward, is a rise in the speeds. So these orbital speeds are getting faster and faster, which means, well, in order not to fall in, the particle has to go faster. And therefore, that means that there's a lot more mass in the middle of that galaxy than what we could account for just by adding up all the stars in the galaxy. So Newton's laws, there should be a capital N there, tell us we should see a rotation curve that looks like this, kind of like the solar system, sort of a Keplerian fall off. As you get far away from the sun, your orbital speed gets smaller and smaller and smaller. But what we actually see is these increasing speeds. And what that means is that there's more matter than we can actually see that accounts for this discrepancy. And that matter is what we call dark matter. It's because we don't have a better term. And so in addition to gravitational lensing, in addition to those rotation curves, there's a number of different pieces of evidence sort of on all cosmological scales that tell us that about 85% of the matter in the universe is invisible. It's not stars, it's not bright, it's not gas. We can't see it using standard model or using standard telescopes. It's there gravitationally, it's pulling stuff in, but we don't know what it is. So we call this dark matter. The biggest piece of evidence is actually the CMB, the cosmic microwave background. And these are the statistics of the CMB. Unfortunately, I don't have time to go into it, but I will answer questions if they come up at the end, because it's a very fascinating piece of physics. And locally, what it looks like, what we think it looks like based on those rotation curves and based on many, many simulations of what just matter that does not interact except gravitationally would do, is that we're sitting in this luminous disk of the Milky Way, sort of halfway out, 8 kiloparsecs away from the center. And that's about 25,000 light years. And we're sitting in this big, fluffy, what's called a halo of dark matter, but you can think of it as just a big diffuse kind of blob that's very concentrated in the center and gets more and more diffuse as you move out. And it's a spherically symmetric kind of thing. It's not a disk like the stars that form a disk. So locally, if we now zoom in even more to where we are within the Milky Way, we can actually compute how much dark matter is at our position by looking at the velocities of all the stars that are around us and figuring out how much matter is actually attracting them on their orbits. Now it works out to be about half the mass of a proton per cubic centimeter. Some absolutely useless astronomer units here. And in British units, which are the most useful, there's about 1 dark matter particle per pint. So, and these particles are flying through us very fast because they're in orbits around the Milky Way center, and we're orbiting around the Milky Way. So what we see is actually a distribution of particles going at sort of a Maxwell-Boltzmann distribution. So some are very fast, some are very slow. And the bulk velocity of this distribution of this gas is coming towards us because we're going towards it. We're orbiting around the Milky Way at about 220 kilometers per second. So this distribution is not co-rotating with the Milky Way disk, but the sun is orbiting around the Milky Way, so we should see this wind of particles, of dark matter particles. What this dark matter actually is, we don't know. We know that it had to be there in the very early universe, so it can't just be like space rocks, because the very early universe was extremely hot and would have melted space rocks. And space rocks needed stars to burn up, explode, and then collapse into planets to actually form. So it has to be something that was around in the very, very early instance of the universe, but we don't really have a model for what that is. And we don't have a model that we know of, that we know is true. There are many models, there are many theories. The one I'm going to talk about here is the WIMP, actually something closer to the WIMP. It's in this island over here, but it's close enough. But it could be something like black holes that were formed in some weird process in the early universe, and there's more weird quantum mechanical things over here. So zooming in again on the WIMP, the weakly interacting massive particle, which is one type of fundamental particle that this dark matter could be. So we're saying we don't know what it is, we just know it's something massive that needs to not interact with light because we don't see it. So it could have a mass to actually be able to produce it with the known laws of physics between 1 and 1,000 GeV, that's roughly between 1 and 1,000 proton masses. It would need to have been produced in the Big Bang with all the other particles. And it interacts very weakly with the standard model particles. So it needs to be able to interact in some way that's not gravitational. So think, probably not electromagnetic, but maybe weak or strong nuclear force, in order to actually produce the particles in the early universe. If there's no interaction, then there's no way to actually make them. And we know there's 5 times more dark matter than there is ordinary matter. But if there is this interaction, then if we're patient enough, we can go and look for it. And this is what's called direct detection of dark matter. So this is the sun, it's flying through the Milky Way at 220 kilometers per second. We're stuck to it here on Earth. And what we see is this wind of dark matter, what we should see is this wind of dark matter coming towards us. It's weakly interacting, so mostly it goes straight through stuff, just like a neutrino would. But it's not non-interacting. So every so often, if you get extremely lucky, a dark matter particle will hit a nucleus in the Earth or in the star and cause it to move. And we can go and look for that very, very rare interaction. And what we do is we take large quantities of very pure, usually noble elements, so to get rid of any kind of radioactivity. We encase it in a very, very, very sensitive detectors. These are all photomultiplier tubes encasing about 3 tons of liquid argon. We shield it from any kind of radiation that would mimic a signal. And then we place it deep underground to get rid of any kind of contamination from cosmic rays and other stuff. And we wait for a dark matter particle to come, bounce off of it and leave. And we look for a little signal from the nucleus being hit. And if we see enough of these that are consistent with our theory, we can say, we've detected dark matter. We don't see any, we've ruled out dark matter with an interaction strength that's so high. So right now, so our signal, the amount of recoils that we'll see, the amount of events, is going to be proportional to the mass of the detector, because it's just the more detector you have, the bigger your telescope is, the bigger your bucket is to collect signals. So I'm going to argue, here's some pictures. Sorry, I forgot about this slide. These direct detection experiments look really cool. This is LZ, which is in South Dakota. This is Cosine, which is in Korea. They're all deep underground, these very deep labs. This is Super CDMS in Snow Lab in Sudbury, Ontario. So I'm going to try to convince you that the sun and other stars are direct detection experiments. Because if dark matter is coming and hitting nuclei in the lab, well, it's also hitting nuclei in stars. And there are a lot more nuclei in stars than there are in your lab, with respect to the deep collaboration. So the idea is that dark matter will come in, will hit nuclei, look at my animation skills. And if a dark matter hits a nucleus and loses enough kinetic energy, it's like a billiard ball interaction, that its velocity is now below the escape velocity from the sun, then it's gravitationally stuck there. It's in orbit, and it's very weakly interacting. So it's going to travel through the gas, only interacting very occasionally, but it can't get out now because it doesn't have enough kinetic energy. It's just stuck. So once it's inside the star, it's going to orbit around, and you'll wind up collecting a bunch of dark matter inside your star. So the mass of the sun is 10 to the 30 kilograms, which is a lot larger than the largest direct detection experiment that we have on Earth, which is a few tons. Mostly hydrogen, 25% helium, 2% heavier elements. That comes in handy. But most of all, it's free. We have a giant detector there that's free. We don't need to build it. We just need to figure out how to listen to what it's telling us. So if dark matter is a particle with a mass, this mass range is important for the science, not really important for what we're talking about right now. A mass sort of around the proton mass, a little bit heavier than the proton mass, then the sun could have accumulated over its lifetime, which is 4.5 billion years, up to 10 to the 47 particles. And that's a lot of particles. So what effect would they actually have on a star? So to figure that out, we need to remember what a star is. So a star is just a big ball of gas. It's denser in the center and less dense outside. And a main sequence star like the sun is generating heat through nuclear fusion. The big ball of gas is trying to collapse under its own gravitation. It doesn't collapse because of thermal pressure, right? PV equals nRT or nKT, which is the grown-up version. Actually, the equation of state is slightly more complicated, but the heat generated by nuclear fusion is pushing out against the collapse due to gravity. And the star stays in equilibrium, but has to continually make more heat because all of the heat eventually escapes into space. And the way that happens in a star like the sun is that you have some fusion, and heat conduction happens by photons just traveling from nucleus to nucleus, like a few millimeters, less than a millimeter at a time, bouncing its way around, eventually going from hot to cold, and slowly over about a million years, making its way to the surface of the sun, where it escapes as sunlight. So fusion energy in, the amount of fusion energy in is going to be equal to the amount of radiation that eventually makes its way out in space. So it's in equilibrium. It's in both thermal and hydrostatic equilibrium. Small amount of energy also leaves the star in the form of neutrinos. These are extremely weakly interacting particles that travel near the speed of light, and we can detect those at detectors like the SNOW experiment in Sudbury. And these are exactly the neutrinos that Art McDonald observed in SNOW that got him the Nobel Prize. So heat is leaving the core via this microscopic radiative conduction in a normal star. And if you're wondering about the temperature profile, so at the very center of the star, it's about 15 million Kelvin. And that drops down all the way down to 5,700 Kelvin at the surface of the star. And you have this temperature gradient, PV equals nRT, so you have a pressure gradient and a density gradient as you go outside of the star. Okay, what does dark matter do? Well, dark matter is very weakly interacting, which means that its mean free path is going to be quite long. So instead of traveling just a millimeter like a photon or like a nucleus inside this really dense plasma, it can travel meters or kilometers or even hundreds of kilometers before it hits anything else. So you can imagine a dark matter particle that's found its way into the core of the sun, gets hit by a nucleus. It's 15 million Kelvin in there, so it's going to start going really fast. And it can make its way out sort of towards the outer layers of the sun before it hits a nucleus again, at which point it collides. The thing it hits is probably colder, has less kinetic energy. So the dark matter is going to deposit its kinetic energy, and that is heat conduction. So it's a non-local way of getting heat from the core of the sun or any star out to the outer layers of the star. And sort of a little bit more, let me finish that thought. So you're transporting heat from the inside to the outside, therefore you're changing the thermal gradient. If you change the thermal gradient because of the equation of state, PV equals nRT, you're also changing the density gradient and the pressure gradient. That's going to change things like the sound speed and the rate at which the sun actually kind of wobbles because it's a big ball of gas. So this is what it looks like more graphically. In the inner parts of the sun, the dark matter will be preferentially absorbing heat, so removing heat from the center. And in the outer layers where the sun is cooler, it's going to be depositing that heat. So then we want to know, well, okay, that's great in theory, but can we actually observe it? So to know if we can observe it and to figure out what the observables are, we need to take a model of how the dark matter actually affects heat transport and stick it into a model of how a star actually evolves. So you need to come up with a model, figure out, code it up, say, if I have a star with this kind of dark matter, what does the dark matter do to the star? And then I run a stellar evolution simulation that goes all the way from sort of a pre-main sequence nebula through the main sequence. And well, we don't actually bother over here. This becomes complicated and we're interested in looking at main sequence stars. But that's still, 5 to 10 billion years of evolution. And at each time step, you need to know exactly what the dark matter is doing to the structure of your star. And that means you need to solve some differential equations. So what are the observables then? I've changed the thermal profile of the star, changed the temperature profile. Therefore, I've changed the density and the pressure. So if I change the temperature in the very center of the star, I actually can affect the neutrino production in the nuclear fusion processes inside the star. You can't mess with the first part. If you know about the PP chain, the first part is you fuse 2 protons into deuterium. That's set by the fact that your star or the sun has to have a given amount of luminosity. But there are different branches of the PP chain that give different types of, or different energies or different spectra of neutrinos. And a few of them are extremely sensitive to temperature. So just a tiny shift in the temperature of the core, we can actually see in neutrino detectors here on Earth. That's one thing. The second thing we can do is look at pressure and density. And the sun being a giant, basically a 3-dimensional drum, it's kind of oscillating back and forth. And you can study the eigenmodes of those oscillations. So figure out what the frequencies of each eigenmode of these oscillations, and there are radial modes and angular modes. You can spend a lot of time doing spherical harmonics and compare your theory with your observation. We have extremely precise observations of the helioseismology, so of those particular modes. And some are very, very sensitive to what's happening in the core. You can go and look at other stars. So if you're smoothing the temperature gradient, if you've taken a bit of astronomy, you know that stars that are heavier than the sun, a little bit heavier than the sun, 1.3 solar masses, have a convective core where the temperature is more or less uniform and heat is being transported by convection instead of radiation. And that's because local hydrostatic equilibrium breaks down and you don't have a nice density stratification, right? The temperature gradient becomes too high and you wind up creating these inversions. But if we're smoothing our temperature gradient by pulling heat from the inside out, by making heat conduction more efficient, then we can actually get rid of those convective cores in some stars. And people have actually looked at data from the Kepler telescope, which was made for looking for exoplanets. But these eigenmodes that we're looking at through astroseismology are very sensitive to boundaries. And if you remove a boundary from your star, so this is just like a wave that's propagating through the star. If you remove the boundary, if you remove the convective zone, you can actually see whether or not a star has this convective zone or not, just looking at the pulsations of the star with a very sensitive telescope. I won't go and explain this graph, but this is basically, if there is no dark matter, your core is extremely uniform in hydrogen composition, and there's a discontinuity in the sound speed, which is what you observe when you observe the pulsations. And when you add dark matter, you remove that discontinuity by just smoothing the temperature gradient. If you have even more dark matter, you can do even more funky stuff to stars. So this is a Hertz-Sprung-Russell diagram. So it's a temperature luminosity diagram, and every star can be placed somewhere on this diagram. The main sequence stars are the ones that are fusing hydrogen, like the sun. So the sun is a main sequence star. And when the star runs out of hydrogen, it becomes a red giant because its core collapses because it doesn't have anything to fuse anymore, and eventually does some little loop-de-loops around here. The lifetime on the main sequence that is therefore determined by how much hydrogen the star has available within its core to burn. So that amount of hydrogen is the amount of fuel inside a sphere that's above the temperature that you need to fuse hydrogen. So if you change the temperature as a function of radius, you're going to change the amount of hydrogen that you have available. So you're going to change the amount of time a star can spend on the main sequence. So when the star exhausts its hydrogen, it leaves the main sequence, and we can't really watch that because it takes billions of years, but you can go and look at populations of stars. So this is my theorist's Hertz-Sprung-Russell diagram. And what you actually see is, well, you look at a map of stars, and the more massive stars, they die earlier, so they move away from the main sequence and disappear. And so the stars right here, these are the ones that are in the process of dying. So from the point, the location of the main sequence turn off, you can figure out how old the population of stars is, and you can compare your model with and without dark matter to what we observe and see if there really is a difference. Now, this is actually a lot more difficult than it looks, and no one's yet been able to do this with simulations of dark matter in stars and comparing with data. And it's something that we're looking to do in the next few years. This is just driving home the point. You can change the main sequence lifetime by having more dark matter, by having this dark matter and heat transport by dark matter. And interestingly, what happens to the star, whether it spends longer or less time on the main sequence, depends on its mass. So it depends on whether or not it had a convective core to begin with. But all of this is wrong, sort of. It's based on some assumptions that are somewhat incorrect. So I told you that to figure out what this dark matter does to stars, you need to first figure out what, in a given time step in your stellar evolution model, what the dark matter is doing to that transported heat. So what we're doing is we're trying to figure out the equilibrium configuration of dark matter and how much heat it's transporting per second from the core outside, and what that looks like is a function of the stellar radius. So we need to do a little bit of math. I won't do a lot, but this is a very nice equation, the Boltzmann equation, because it describes actually everything, just because it's so general. What you need to do is solve this Boltzmann equation, which tells you the phase space distribution of the dark matter that's accumulated in the star. And once you know that, then it's very easy to calculate what each one of those dark matter particles is doing at any given time. So the phase space distribution is just how much dark matter there is as a function of radius, so r, and what those velocities are at what the distribution of velocities are at every single radius. So a Maxwell-Boltzmann distribution, for example, is a phase space distribution, at a uniform temperature. It's telling you that everything is isotropic and that the energies of all your particles follow an exponential. So this equation, this Boltzmann equation, can be used to describe the distribution of anything. It's on the left, a bunch of derivatives. So it's called the Alluvial operator, but it's just how much is my phase space distribution being affected by evolution of time, gradients, and any external forces. And on the right is what's called the collision operator, which is what happens when every particle is scattered from velocity v to any other velocity, and how many particles are being scattered from any other velocities to velocity v. So it encodes a lot. And if you want to write it out, well, there are 3 velocities, because we're in 3 dimensions. There are 3 dimensions, because we're in 3 dimensions. It does simplify because we're in spherical coordinate, we're spherically symmetric, a star is spherically symmetric, so we can actually ditch a few of those. And it could depend on time if you weren't looking for the steady state. Fortunately, we're looking for the steady state. So in principle, it's a 6 or 7 dimensional integral differential equation that you should solve consistently at every single time step in stellar evolution. Now, there's no analytic solution to this. You can't just go and derive a solution. And just to show you what it looks like when you expand it out a little bit, this is it. So you have a bunch of derivatives on the left-hand side. This is accounting for gravity. This is, diffusion. And on the right-hand side, you have integrals over all possible collisions in and out that change the velocity distribution of all your particles. So it becomes a bit of a mess. So we can understand this Boltzmann collision equation through a couple of approximations, either when interactions are very, very strong or when interactions are very, very weak. So collisions are very frequent or very infrequent. If they're infrequent, if the interactions are very weak, then the particle is going to travel a very long way before it interacts. So it can conduct heat a long distance, but if you just keep tuning down the coupling, so making the mean free path longer and longer, that means that its chance of actually hitting anything becomes very low, and the efficiency of this heat conduction becomes low. On the other end, when interactions are very strong, then the dark matter particle is basically stuck inside the plasma. Can't really go anywhere. It's hitting stuff all the time, but it's not really doing much. So things become very, very inefficient as you go to very strong interactions as well. That's like what the photon's doing. So somewhere in the middle, there has to be some balance where the interactions are frequent enough that you're getting somewhere, but you're also not trapped. So you're efficiently conducting heat from one place to the other. And this is called the Knudsen peak. This is where the optimal heat transport is happening. And this is a property of the microphysics, of the particle physics of the dark matter, which is what we're trying to discover and understand. So just more graphically, I've switched these around. That's not very nice of me. So the way in which we're going to model these things, on the right, we have our isothermal, or our very weakly interacting conduction. So the heat conduction efficiency is this curve here as a function of, just think of this as the mean free path on a log scale. So large mean free path, not very efficient. Small mean free path, not very efficient. And the way in which we model this is going to depend on where we are in this curve. And so we can calculate what happens here. We can calculate what happens here with some approximations. And I'll tell you about those, because this is what people use. But over here is a giant mystery. And this is where the effect is the largest, and this is what we'd like to look for. So I'm going to very briefly go through these two schemes just to set up how this works. So in the very weakly interacting, your particle is stuck regime, you can basically model your dark matter as a single kind of fluid that's sitting in the star. It's like a heat bath. And so you have this fluid that's in contact with the star, which is at different temperatures at different radii, and it's transferring heat, and the amount of heat being transferred is just temperature of the star minus temperature of the dark matter. This has been known since 1984. It's formally incorrect, and we've known that for 30 years, but it's still used because it's very easy to implement. And by easy, I mean not impossible. All right, so where the temperature of the dark matter is higher than the star, the dark matter will be heating it. That's right. It's depositing heat. And where the temperature of the dark matter is lower than the temperature of the star, well, the dark matter is just taking some of that heat away from the star. So it's very simple, very, very easy to understand what's going on. Sigma here is the cross section, if you know what a cross section is. Otherwise, it's sort of the inverse of the mean free path. The second approach, if you're in that very kind of almost stuck regime, it's called the local thermal equilibrium regime, you can kind of think of your heat conduction as, I have a little bit of an anisotropic distribution of velocities. That is to say, the velocities are a bit higher away from the center of the star than they are tangentially to the center of the star. So that overall is giving you a bit of a kick, a dipole that's pushing heat from the bottom outwards, from the core of the star outwards. And the way this is done, so you take this awful Boltzmann collision equation, you expand it in a Taylor series, perturbative expansion in this quantity. So this is mean free path, which is very small, times the gradient of the temperature, because why not? And then you expand it in Legendre polynomials, which gives you a nice, beautiful, invertible expression for the heat conduction rate and the density of dark matter in the star. It's not correct near the center because the dipole thing breaks down, because if you're at the center, you're not bringing heat from bottom up, you're bringing heat outward everywhere, so it doesn't quite work. It's more correct than the previous approach. It's also very elegant, and extremely numerically unstable if you want to actually implement this in a simulation. So we have these two approximations, and we have no idea what happens here, and we're left with sort of having to bridge them with sort of analytic fudges. And what we wanted to know when we started this is, are these approximations even correct? Because no one has actually gone and solved the Boltzmann equation completely and figured out how correct these are. So now we get to Monte Carlo, and I realize I'm lowish on time, but I promise I'll try to be quick-ish. What is Monte Carlo? Monte Carlo is a neighborhood of Monaco. It's where a lot of casinos are, and casinos are known for random number generating. So Monte Carlo is really just solving a problem by very cleverly using random numbers that simulate some process that will asymptote towards the solution to your problem. So let me try to explain that again. We're looking for the steady state distribution, so the distribution of particles, of dark matter particles, as a function of their radius inside the sun, and as a function of their velocity, and from that we can figure out how much heat is being transported, and so on. We want to know the amount of heat transported per unit time by these dark matter particles. And we're going to use what's called ergodicity. If you've seen this, you think it's absolutely amazing. You should. If you haven't, ergodicity means that if I want to understand the distribution of a bunch of particles in equilibrium, it's sufficient to take a single particle and just watch it bounce around for a very large amount of time. And as t goes to infinity, that particle will occupy every position in this 6-dimensional phase space. It will eventually occupy all of the positions of the particles that you would expect to make up a distribution of particles in steady state. So the behavior of a system can be deduced from the trajectory of a single particle just bouncing around for long enough. So if we can simulate the trajectory of one of these particles for long enough, that will tell us what the particles as a collection will do in the sun. So we build a Monte Carlo simulation. We simulate a random walk of particles going around the sun. So the first thing you do is you take a particle, randomly place it inside the star. You say, this guy was just captured. Let's see what happens. You give it some position and some velocity. Now you randomly choose an optical depth. So how many mean free paths is it going to travel before colliding with a nucleus? So that's where step one of the Monte Carlo comes in. Then you integrate its trajectory, given the gravitational potential that it's stuck in, until that point, until it hits that number of mean free paths. And then you say, okay, stop. This is where you're colliding, because these collisions are a stochastic process. And then you collide, so you transform to the center of a momentum frame. And in the center of a momentum frame, collisions are isotropic, so you have an equal chance of scattering any direction. You randomly pick a direction to scatter in, and then you transform back to the star's frame, and you repeat. So this particle is going to travel, collide, travel, collide, travel, collide, travel, collide. So this is what it looks like. I'll show you a couple of little videos. If you have a short mean free path, so each segment is the path between collisions. The paths don't look curved from the orbits because they're very short. So they're almost straight lines, except that one here, we got a bit lucky and the particle went a very long way before colliding again. But you can see the short mean free path, the particle is kind of stuck near the center of the star. This is about 10 to the 5 kilometers. The radius of the sun is, well, 7 times that. This is a few hundred collisions. If we look at 50,000 collisions and just put a point for every single collision, we start to build up what the collection of dark matter particles inside the star would look like. So 50,000 collisions for this particular mean free path would be a couple of weeks for a typical particle. If you have long mean free paths, you have many, many orbits before each collision. I meant to make this look a little bit better. It looks a little bit choppy. The choppiness is because of is numerical, it's not real. But the particles are describing just loads and loads of orbits before they collide, and when they collide, change direction, and then go on a few orbits, change direction, go on a few orbits. This is funky, so let's look at it again. So you wind up with this very non-local heat transport where you're going sort of in and out or around the sun a large number of times. And after 50,000 collisions, again, you describe this fluffy distribution of what the dark matter should look like. And in contrast to the previous one, which is 2 weeks, this is 1,000,000 years, same number of collisions, just very long mean free path between each collision. Okay, more importantly, we can just histogram these distributions, histogram these distributions in terms of radius and get a distribution of the dark matter particles, and the simulation and the theory look like they agree very, very well, where you should be versus where your particles actually wind up. And we can figure out the heat transported by dark matter. And to do that is very easy. It's just the amount of heat transported in a collision, the amount of energy, is just 1/2 mv squared before minus 1/2 mv squared after. So you're removing heat from the center of the star and you're depositing it here. And this is the thing that we're trying to calculate by hand with those approximation schemes. And the Monte Carlo is there to give us an exact solution, takes a long time, that we can compare our theory to. So let's do that. A few million CPU hours later, we want to simulate a lot of different stars, a lot of different dark matter parameters. If we look at the data, so these are all data from the Monte Carlo. This is radius. Just look at the one on the right-hand side, actually. Ignore the luminosity here. This is heat removed from the center of the star and heat deposited, small mean free path, large mean free path. Now, we can connect it, we can add the theory calculations on top of it. And here, one of them does well, the one we expect, that's good. Here, one of them can be corrected to do well. The other one's off by a factor of 2. Okay. So the theory is, it's not great, but it's not terrible either. Let's look at a different type of particle physics interaction, because particles don't always interact with as billiard balls. So let's look at, say, something like a Coulomb interaction or something like that. So you get the same thing. These luminosities, they're telling you one thing, but you can still look at these little insets here, which are the heat transported as a function of radius. The numbers don't really matter. Let's compare it with the theory. And if you look at these, every single theory line is wrong. Stuff is not going well. But we have the correct answer now. So we can take this and we can adapt the theory and come up with a new scheme that's based on these Monte Carlo results. The new scheme happens to be quite simple and physically makes sense. I don't have time to get into the details. They're not too important here. But from that new scheme, we can go in, recompute the theory, and compare it with the Monte Carlo data, which is the true solution. And that's the blue lines here. And as you can see across a wide range of interaction strengths, the blue line fits perfectly. And it's not a fit. This is a prediction. So I plug a number into the theory, I load up the data from the Monte Carlo that Hannah sent me, put the two together, and this is the answer. There hasn't been any fiddling up and down with the curve or anything like that. And notice the orders of magnitude differ by a lot from one to the other. So we've learned that the previous 30 years have used incorrect curves to simulate the effect of dark matter on stars. The general trend is all right? These are the other ones. The general trend is fine. But so here are the ones that are absolute disasters. But we don't have any results from previous papers that precisely tell us what dark matter does to stars. But now at least we have the tools to do it, and we know that it's correct. This is just driving home the point. If you look at the interaction cross-section, so mean free path, and these are just different types of particle physics interactions. The predictions, which are our new theory, is the solid curve, and the data points from the Monte Carlo simulations. You might be wondering about the error bars. That's just because you need a lot of collisions to converge to the correct answer, and sometimes a lot is a lot, right? It could be up to 1 billion collisions, which is a load on our servers. So that's why the error bars are quite large, the statistical errors. But we now have something that is can be used in stars. So now that we understand dark matter, how dark matter conducts heat in a star, we can use our fast new theory, our analytical model, to model heat conduction in a large-scale stellar simulation, calculate the response of the star itself. So 30 years after the first attempts, we're confident now that we have the physics right. And we can, the next step is to actually go back and put this into the model of a star and figure out, well, what kind of effects this dark matter has on stars, and then go and look for those effects in data, possibly including new JWST data. Should be really cool. There's some helioseismology and very short summary. So signatures of dark matter that we search for in underground laboratories could also show up in stars. And we need a theory basis to understand what observables that we look for. So this process has all been about putting together that theory basis and validating it with simulations. And we're also working on a follow-up to do this with very different types of stars as well, to see how well the theory holds up. It's been a lot of fun. So a lot of coding. And if you're interested in looking at more from our paper, here's the link to the archive version. So thank you very much.
Amazing. Thank you so much, Professor Vincent, for spending this evening with us and for that wonderful presentation about using Monte Carlo to find dark matter. Now, before we move on to the Q&A session, I want to remind everyone to please make sure to register for our next session of the Physics Hour with Dr. LeBlanc as we explore quantum technologies with atoms. I'll just stop the recording.